If you throw a baseball straight up into the air, it climbs, slows down under Earth's gravity, and falls back to your glove. Throw it at 11.2 kilometers per second, however, and it will escape Earth's gravity forever. This boundary is known as escape velocity. But what happens if an object becomes so massive or so incredibly compressed that its escape velocity surpasses 300,000 kilometers per second? That is the speed of light, the ultimate speed limit of our universe. If light itself cannot move fast enough to escape this object, then nothing can, rendering the object completely invisible to the outside world. In 1915, while serving on the Russian front in World War I, physicist Karl Schwarzschild solved Einstein's field equations of general relativity. He discovered that any mass, if compressed tightly enough, will collapse into a mathematical point of infinite density. The boundary surrounding this point is called the Schwarzschild radius, calculated as 2 times the gravitational constant times mass, divided by the speed of light squared. For our Earth, this critical radius is just 9 millimeters, about the size of a marble. If you could squeeze the entire planet's mass into a sphere smaller than that marble, it would spontaneously collapse into a black hole. To understand why this happens, we must discard the Newtonian idea of gravity as an invisible pulling force. Instead, Albert Einstein showed that mass curves the very fabric of four-dimensional space and time. A normal star like our sun creates a gentle depression in this fabric, causing planets to orbit around it like marbles rolling around a bowl. But as a massive star dies, exhausting its nuclear fuel, it can no longer support its own weight against gravity. The star collapses inward, stretching the space-time fabric deeper and deeper until it forms an infinitely deep gravitational wall from which no path leads outward. A black hole consists of 3 main anatomical features defined by general relativity. At the absolute center lies the singularity, a point where gravity becomes infinite and our current laws of physics completely break down. Surrounding the singularity is the event horizon, the point of no return where the escape velocity exactly equals the speed of light. Finally, rotating black holes feature an external region called the ergosphere, where space-time itself is dragged in, a phenomenon known as frame dragging. In this region, objects must move faster than the speed of light relative to a distant observer just to remain stationary. Since black holes emit no light, how did we capture the historic image of M87's black hole in 2019 using the Event Horizon Telescope? The answer lies in the extreme physics occurring just outside the event horizon. Gas and dust are pulled into a rapidly spinning structure called an accretion disk, heating up to millions of degrees through friction and emitting intense X-rays. Furthermore, the immense gravity of the black hole acts as a gravitational lens, bending and warping the light from behind it. This creates a highly characteristic bright ring of light framing a dark circular shadow, which is a silhouette of the event horizon itself. In 1974, Stephen Hawking introduced quantum mechanics into this gravitational picture, revealing that black holes are not completely black. Due to quantum fluctuations near the event horizon, virtual particle-antiparticle pairs are constantly created. Occasionally, one particle falls into the black hole while the other escapes as thermal radiation, known as Hawking radiation. This process causes the black hole to slowly lose mass and eventually evaporate entirely. This introduces the profound black hole information paradox. If a black hole evaporates, all the physical information about the matter that fell inside is seemingly destroyed forever, violating a fundamental law of quantum mechanics.